In this video, we're going to look at molecular structure and acid strength. Okay, so there are a couple things we need to consider when we're talking about how molecular structure can be related to acid strength. The first thing is the polarity of the bond in which the hydrogen that's leaving or becoming deprotonated is bonded to. So for instance, if we have a binary acid, so a substance in which we have hydrogen and one other atom, such as fluorine, chlorine, bromine, or iodine, then we can simply consider the electronegativity of the atom that's bonded to the hydrogen. So we need to consider the polarity of the bond, which is based on the electronegativity of the atom that's bonded to hydrogen. The other thing that we need to consider is the size of the atom. Okay, so if we think about general trends, let's look at the electronegativity here. As we go from left to right across the periodic table, in general, we see an increase in the electronegativity, and we see a decrease in the electronegativity as we go down a group in general. The atomic radius, okay, if you recall, as you go down a group on the periodic table, the atomic radius tends to increase, and as you go from left to right across a period on the periodic table, the atomic radius decreases. So both of these factors play a role in the bond strength. Okay, so we're talking again about the hydrogen X atom, whatever that atom is, bond strength. This is going to be related to the acid strength. Okay, so again, those two things, the polarity of the bond, which is related to the electronegativity of the atom that's bonded to the hydrogen, and the size of the atom play a role in the bond strength. And a strong hydrogen X atom bond leads to a lower acid strength. So that means that that bond is less likely to break, and we need that bond to break in order to have a strong acid. A strong acid is signified by having complete dissociation of the hydrogen whatever atom. Okay, so if we have a strong hydrogen X atom bond, that lowers the acid strength. There's less proton generated in the reaction. Okay, so one of the trends that we see then is that a more polar bond has a lower bond strength. Okay, so it's a weaker bond. Okay, therefore that acid is stronger. And so if we consider two acids, we have acetic acid and sulfuric acid. Okay, these structures are shown here. Sulfuric acid is H2, here's our two hydrogens, SO4, here's our sulfur and our 4 oxygen atoms. And then acetic acid, we have 2 carbons, 4 hydrogens, this one is the one that leaves, and then 2 oxygen atoms. This is a carboxylic acid. And we've drawn electrostatic potential maps around these two substances. And so keep in mind when you're looking at the electrostatic potential map is that regions that are red have a high amount of electron density, and regions that are blue have a low amount of electron density. And so those and the colors in between signify sort of those colors in between signify medium sort of electron density, somewhere in between. Okay, so if we look at and compare these two acids, we're interested in one of these hydrogens leaving on the sulfuric acid and this hydrogen leaving on the acetic acid. Okay, we know that H2SO4, at least the first proton leaving, is a strong acid. Okay, and acetic acid is a weak acid. And we can glean that information from these electrostatic potential maps because there is more red on the oxygen that's bonded to the hydrogen, meaning there's more electron density here on this oxygen than on the hydrogen, and there's a larger difference sort of in color than there is on the acetic acid. So you don't see as much red over the oxygen that the leaving hydrogen is bonded to in the acetic acid. There's less of a difference in the electron density, which means this hydrogen is less likely to leave. This is a proton that's less likely to leave than is this proton. Okay, so we saw the example where we have a polar bond. Both of the oxygen-hydrogen bonds here are polar, but this one is more polar than in the acetic acid. And so that has the more polar bond in the sulfuric acid has a lower bond strength, signifying we have a stronger acid. Okay, the other trend is that as the size of the atom increases, the bond length decreases, which gives us a weaker bond, which in turn gives us a stronger acid. So this trend is useful when we're considering or we're comparing acids as we go down a group in the periodic table. Okay, so we said as the size of the atom increases, that's going down the periodic table, the bond length, Alright, so we saw with the sulfuric acid and acetic acid example where we both have oxygen-hydrogen, polar oxygen-hydrogen bonds. The more polar bond was on the sulfuric acid, so this is a more polar oxygen-hydrogen bond, and that gives that bond less strength, lower bond strength, and so that gives us a stronger acid. The other example is where we have the size of the atom that's bonded to the hydrogen changing. So this is useful when we're comparing binary acids that are created from elements that are relative to each other down the group. So for instance, HCl, HBr, HI. Okay, in these examples, considering if we want to think about the acid strength, we need to consider the size of the atom. And as you recall, as we go down the group in the periodic table, the size of the atom increases, which means that the bond length increases, and that gives us a weaker bond. And when we have a weaker bond, we have a stronger acid. So if we consider the energies in the bonds between the hydrogen and fluorine, chlorine, bromine, and iodine, we can see in general the general trend where the bond strength is decreasing as we go down the periodic table. And again, that's because the size of the atom is increasing. So HF, which has the strongest bond, smallest atom in that in this group of 4 atoms, they're in strongest. This is the weakest acid in this selection of binary acids. In fact, it is a weak acid, whereas HCl, HBr, and HI are all strong acids. Okay, so you can see the effect here of the size of the atom. Okay, so if we look at this again, the strength of the binary acid, so the acid strength, HI is greater than HBr, is greater than HCl, is greater than HF. And that's because the bond enthalpy is decreasing, the bond strength is decreasing as we go down the group. So the strength of the hydrogen atom, X-atom bond, HF is greater than HCl, is greater than HBr, is greater than HI. So these general trends that you've already seen, the strength, the atom size, atomic size, and the electronegativity or polarity of a bond, play a role in the strength of an acid.